2.7, we're gonna talk about using absolute value functions and transformations. Okay. Parent function for absolute value function is simply the equation f of x equals the absolute value of x. Those two bars mean you're taking the absolute value. What does the absolute value mean? When you're taking absolute value, what do you always get out? A positive. A positive. You always get a positive out. If you take the absolute value of something, it's basically saying what's the distance from this point to that point. It's always a positive out. Our graph can be negative if there's a negative on the outside of an absolute value. But if there's no negative on the outside of an absolute value, you always get positive answers out. So if I put in a -2, I get a positive number out. If I put in a +2, I get a positive number out. So if I plug in positive numbers, when I go to plug in those same same negative numbers, I'm going to get the same output. Meaning my graph creates a V because they're going to correspond back and forth. Okay? So an absolute value graph is always a V. It intersects at a vertice. Okay? It comes together at a vertice. That vertice is known as the vertex. Okay? The vertex. When you have a simple absolute value function with nothing added to it or subtracted to it on the inside or outside, your vertex is always 0, 0. Okay? We're going to talk about when that shifts, what that looks like also. But your vertex should always be 0, 0 in a parent function. Okay? And your vertex is the starting point. If I plug in a 1 to this, I get a 1 out. If I plug in a -1, I get a -1 out. If I plug in a 2, I get a 2 out. If I plug in a -2, I get a +2 out. Okay? So it's always going to be mirroring itself. It's going to have perfect symmetry. And your line of symmetry goes through the vertice, through the vertex. Oh, shoot, I forgot to do it. Oh, no, I did this on purpose. Okay. You can derive new absolute value functions from parent functions through things called transformations. Transformations we talked about last year in geometry a lot. What happens when you do a transformation? What type of transformations are there? It moves, but be more specific. Use better language than that. What type of transformations were there? Okay, rotation's a transformation. Good. What else? A translation. What's a translation specifically? What's it do? Yeah, it just shifts up or over. It slides. Okay? So a lot of our transformations for absolute value are going to be translations. They're just sliding up and down or over left and right. Okay? Now, this form right here, y equals the absolute value of h minus k plus x. Okay? That is a translated graph because our normal graph is just y equals the absolute value of x. Okay? Your h and your k tell you your vertex, your new vertex. Okay? So the h is always opposite of whatever it is. So if it is negative on the inside, it is a positive number. Your k is whatever it is. Okay? And your k is your y. So your h is your x, k is your y coordinate. It's your new vertex. From there, I can graph. Okay? So if I know that my new vertex is right here, I'm only going to graph numbers on this side of it and this side of it and create my absolute value. In fact, all I need is a vertex and to graph a positive and a negative number, and then I can just make my V off of it. Okay? It's really simple when we go to graph. So it says compare y equals the absolute value of x plus 4 minus 2 to the graph of y equals the absolute value of x. What do you know about that one? We're going to graph the parent function first. What's the vertex? 0, 0. And if I input a 1, I get a 1 out. If I input a -1, I get a -1 out. If I input a 2, I get a 2 out. If I input a -2, I get a +2 out. Here is the parent function of that graph. Yes? Now, look at this one. Y equals the absolute value of x plus 4 minus 2. What is my vertex? You always have to graph your vertex first. What is my vertex? No. You were right the first time. Your vertex, look. look right here. This says negative HK, and what was it? HK. It's opposite. Whatever's inside with your X is opposite. So what is my vertex? Negative 4, negative 2. So here's my vertex of this one. I go down, I go 1, 2, 3, 4, and I go down 2. That's my vertex. Now, I just plug numbers in to get my inputs and outputs. I'm going to plug in a negative 3 and a negative 2. Okay? If I plug a negative 3 into this, what's negative 3 plus 4? 1. And what's 1 minus 2? So I get negative 3, negative 1, right? Negative 3, just lay it on my desk. Negative 3, negative 1. Thanks, Alex.
Yeah.
And remember that this reflects over that vertex, okay, because that's a line of symmetry. So I can plot my other point without plugging in a number. So if this is at negative 3, my next point is going to be, technically there should be a line right there. It's going to be 1 unit away from that, which is negative 5, negative 1, okay? Technically, I don't need to plug in any other numbers. I can literally graph from here. Now, compare it in words for me.
Oh, that's funny.
Oh, I know. Compare it in words for me. What happened? Compared to the parent function, the equation y equals the absolute value of x plus 4 minus 2 is what? What happened to it? Translate at what? Down 2 and left 4. Okay, so give me words and give me picture. Okay, give me words and graph. Okay, here's another one. Stretching and shrinking. Okay. When you have the graph, the parent function y equals the absolute value of x. Okay. If you have something on the outside of the absolute value of x, say a whole number, okay? Or say you have a fraction on the outside. Do you know what the whole number does on the outside? Anybody have a guess? What happens when I take, let's say this is 1. What's the absolute value of 1? And what's 1 times 3? So what is it doing? It's multiplying, which is doing what to that graph? Instead of 1 being my output, 3 is my output. What happened there? Think. Just spit out any idea. It didn't reflect, but there is a way that it does reflect. We'll talk about that in a second. What happens if something is 1 unit, but now it's 3 units? What happened there? It got bigger.
But it can't be small.
But it can get smaller too, so it got bigger. It stretches the graph, okay? When you multiply by a whole number, it is stretching the graph out. Because instead of it being at 1, it's stretching it to 3. So instead of being 1, 1 right here, it's going 1, 3. It makes it skinnier, stretches it. What happens if there's a fraction on the outside? It's getting smaller, it's shrinking it, it's making short and fat, okay? Because now with 1 as my input, 1/3 is my output. So it makes it short and fat. If there's a whole number in front of it, it stretches it. If there's a fraction in front of it, it shrinks it. And that's the terminology I need you to use, stretching and shrinking. Okay? Now, and if I have a negative in front of it, like this, that's when it flips it. And it flips it over the x-axis. So it faces down. Anytime there's a negative, my V is facing down. It looks like a mountain now, okay? And that's all explained right here. When A, what's in front of that absolute value sign, is negative, it reflects it over the x-axis, okay? When A is greater than the number 1, it vertically stretches it, okay? It gets narrower. When A is less than 1, it vertically shrinks it. It gets wider, okay? So we're gonna graph these and compare them to our parent function. Let's graph the parent function again. My vertex is 0, 0, my outputs are 1, 1. I'm gonna make this 2, so that I can have a little bit more space. 2, 2. Put some more lines in here. So I graph it, it looks like this, yes, parent function. Remember, we're always graphing, we're always writing in words. Now, I come to this graph. It says graph y equals 1/2 absolute value of x. Where's my vertex? Always graph your vertex first. Where's my vertex? Yeah, there's no h and k, right? There's nothing being added or subtracted inside of the absolute value, nothing added or subtracted to the outside. So it stays 0, 0. Now, when I plug a 1 in, what do I get out? Times. So, yes. So if I plug a 1 in here, I get a 1/2 out. Okay, if I plug a 2 in, what do you get out? 1. So, if I plug in a 1, I get a 1/2 out. If I plug in a 2, I get 1 out. This reflects over, okay? This reflects over. This is what happens to that graph. You guys have graphing paper, it will be easier too. Okay, so now tell me in words, how does that compare to the parent function? It is wider by how much? Yes, I need you to be specific. You have to say the graph is wider by 1/2 a unit. Okay, by 1/2. Now, let's graph this one. Y equals -3, the absolute value of x. Where's my vertex? 0, 0. What do I know about this graph automatically? It's going to flip down because that negative is there. What else do I know about this graph automatically? What's the 3 tell me? It's going to stretch, it's going to get skinnier, okay? If I plug a 1 in here, what do I get out? I get the absolute value of 1, and then 1 times -3, so you get, so if I go 1, -3, and then reflect it over, and look at this graph. Okay, so now tell me in words, what happened there? Yep, it reflected over the x-axis. It's stretching by a unit of, well, just 3. The negative is when you say it flipped over the x-axis. The 3 is what it's being stretched by, okay? Okay, got some more. First, graph this parent function again, like always. 0, 0, 1, 1, 1, 1. I'm just gonna do it like that because we'll save some time. Now, here. Okay, there's a lot going on there. First of all, what automatically has changed? What do we know by looking at that? What's changed? What's going on? We have an HK now, good. What'd you say? Our vertex switch. So what's our vertex now? 1, 3. Our vertex is 1, 3. So we need to graph that first. 1, 3. 1, 3. 1, 2, 3. Okay? Vertex is 1, 3. What else do we know by looking at that graph? It's going to be flipped. It's going to face down. What else do we know about that graph? It's going to stretch by how much? 2. Beautiful. So now we just plug numbers in. Since this was a 1, I'm going to plug in a 2. Does that make sense? 1, 2. Okay. So I'm going to plug in a 2. So I have -2, the absolute value of 2 minus 1 plus 3. What's the absolute value of 2 minus 1? 2 minus 1 is 1. Absolute value of 1 is 1. What's 1 times -2? And what's -2 plus 3? So I have 1, 1, right? Oh, I plugged in 2. You're right, I lied. I have 2, 1. So this is 2 and 1. And that's going to reflect over this, right? Now if my graph was even, it would be better. But so then this is my absolute value graph. Okay, now in words, tell me what happened. You You basically already have. Tell me what happened in words, everything.
How do you get the two?
You just plug a number in. I picked 2 because this is my vertex is at 1, 3, so I have to pick a number either left or right of it, and I just picked positive 2 because it's easiest.
Okay.
So tell me in words what happened. It didn't shrink. And it stretched. It stretched. What else happened? It stretched by 2 units. It flipped down. Good. Reflected down. What else? There's one other thing. The vertex shifted what way?
Right.
Right 1 and up 3. Right 1 and up 3. Perfect. Now they give us a word problem dealing with it. This right here is actually a vertex, or a absolute value function. I'll help you look at those numbers in a second. It says in calligraphy, light from a laser beam is split into 2 beams, a reference beam and an object beam. Light from the object beam reflects off an object and is recombined with the reference beam to form images on film that can be used to create 3-dimensional images. Write an equation for the path of the reference beam. So we're going to talk about how to write an equation. Now, what is our equation for absolute value when it's not a parent function? Y equals what? A, absolute value of
Minus
H, and then what?
plus K.
So, to write an equation of this, I literally have to find my vertex and I have to find my A. That's all. Okay, let's talk about how we do that. First, the vertex shouldn't be too hard. It's right here. Now we have to look at that because I know you can't see those numbers and I can't either. But the numbers are 5, 8. Okay? 5, 8. So if that's my vertex, where do I plug that into this equation?
H is on 5.
Yep, H is gonna be 5 and
K is on
K is gonna be 8. So if I plug this in, I should have right now Y equals A, X minus 5, because I just plugged 5 in there, and then plus 8. Okay, so far I've got that. Now, the only other thing we need is that A, correct? Okay, so let's talk about how you get A. A is really simple. Here's how you're gonna get it. You're going to take a point on that graph anywhere, and you're gonna plug it in for Y and X and solve for A, like we did for indirect variation. Remember how we had Y equals A times X and we just take a point and plug it in? Okay, now this one makes it really simple, because what point is the easiest to plug in that's on that graph? 0, 0. So if I say 0 equals A, 0 minus the solve this with me, okay? What is the absolute value of negative 5? 5. So I get 0 equals 5A, right? Because I have A times that absolute value. Plus 8. Now what do I do? Subtract 8. Good, Keaton. Subtract 8 from both sides. So that I get negative 8 equals 5A. Now what do I do? Divide by 5 and you get, what? What do we get? A equals what? Negative 8 over 5. Should it be negative? Yeah, because look at our graph. What do we know about that graph? It's doing what? Facing down. So it should be negative. I should have a negative. So that's beautiful. So my equation comes out to be, my final equation is Y equals negative 8/5 X minus 5 plus 8. Does that make sense? It's not super hard, okay? You just have to look at all the pieces. We're gonna do a couple more things. Okay. This one here is not an absolute value function necessarily, okay? because it's only like a portion of our function, it's not a whole thing. So this is transformations of general graphs, okay? We can apply what we just learned to absolute value to any type of graph. If I have an H and a K, I have a new starting spot, okay, compared to the original. If I have a negative in front, it's flipping, okay? If I have a whole number in front, it's stretching. If I have a fraction in front, it's shrinking, okay? To any graph that we graph this year, period. Those are the rules for any graph. So if you can recognize those things, graphing will be much easier this year if we get that through our head. New starting spot is always HK. Remember, H is always opposite of what it is, but K is the same. We shrink if there's a fraction in front. We stretch if there's a whole number in front. We flip if there's a negative. Okay? If you can remember those things, you can graph anything this year. Okay? So we start with an example. They say the graph of the function y equals f of x is shown. This is the graph that they have for us. Okay? Then they come down here and they say, tell me and sketch the graph of y equals 2 times f of x. Okay? So what do I know of part A? What's going to happen to that graph? Stretch by 2 units, okay? So how we stretch it by 2 units is this, okay? That says y equals 2 times f of x. So we take whatever the y values are and we multiply them by what do you think? 2, by 2. We do not do anything to the x values because remember, I'm still plugging in the same number for x because if I plug in a 0 here, what do I get out? Yes, so my vertex is still the same, okay, if I plug in a 0. If I plug in a 1 here, what do I get, or if I plug in a 2 like they did. If I plug a 2 in here, well, let's see here, is that what they plugged in? I got 2, 3, so then if I plug in a 2 to that equation, because they got a 2 out when they plugged in, or when they plugged in a 2, they got a 3 out, then I have to multiply that 3 by 2. So what do I get out when I plug in a 2 in this case?
The 2 on the
So
x.
if my x is 2 still, what's my new y? Not 3. On my original function, it was 2, 3. What is this graph growing by? 2. So this time if I plug in a 2, what is my output for y gonna be? No. Listen, it's very confusing because they don't give you an equation to work with. They just say y equals f of x is the line shown. So you have to look at the points here. When they originally plugged in a 2, they got out a 3. You told me this is stretching by how many units? 2. Stretching by 2 units because there's a 2 out here. So this time when I plug a 2 in, this is going to stretch by a multiple of 2. Meaning I'm multiplying something by 2 because it's going to stretch because I'm multiplying by 2. If originally I got a 3 out, what is my new output? 6. So I go to 2 and I graph 6. That's 3, 4, 5, 6 would be up here, right? Now over here I had plugged in a 5 and got a 3 out. So what is my graph growing by again? If I plug in a 5, I'm going to get what out again?
No. You need to multiply by 5, right?
You don't multiply the 5, you multiply the y. You multiply the y, not the x. So it's going to be 5, 6. 5, 6. So 5, 6. So my graph looks like this. Look, it's stretched by 3 units. 1, 2, 3. It's 3 higher. It's stretched. It's twice as high. It did stretch by 2. It's twice as high. When you're stretching, you're multiplying, so you have to think in that form. It's twice as high as the original one. Okay? It's confusing when they don't give you an equation, so you have to think and use the points they give you. Down here, okay, this one says that y equals negative f of x plus 2 plus 1. Okay? What do we know is going to happen to this graph? Just looking at that equation compared to the original one, what's gonna happen? Flip, and what else? Your vertex does what? Shifts up one and what? And left two, because there's a 2 with that x. So my new vertex, let's start there. What's my new vertex? -2, 1. Okay, so I go to -2, 1. Here's my vertex. Now, we have to think, this was my original point, and what's it doing? Flipping. It's flipping. So if I flip the point 2, 3, if I reflect it over the x-axis, which we did all year last year geometry, if I reflect it over the x-axis, what's the pattern for that when you flip something over the x-axis?
The y changes.
Sort of. Yeah, the x stays the same, the y changes. What do you mean the y changes?
Isn't it the opposite?
Good. So instead of being 2, 3, my new point's gonna be 2, -3. Beautiful. 2, -3. So 1, 2, 3. We're gonna pretend that that's right there. Instead of being 5, 3, it is. Yeah, 5, -3. And I have graphed that equation, that shift. Okay? Those are the tricky ones. There's not a ton like that on your homework. Almost all of them are gonna be absolute value. Okay? Absolute value is much simpler to me, because it gives us, oh, I know what we did. Let's graph this. Let's graph one more thing. Let's graph this. -1/2. Absolute value of x. How do I graph that? Always start with your vertex. Vertex is -1, -3. -1, -3. Okay, now what? It's flipping, so which way is it gonna face? Down. And the only other thing I need to do is plug in a number. That's all I have to do. Now personally, because I'm not on 0 for my x, I'm gonna plug in a 0. So that's an easy number to work with, yes? So if I plug in a 0 to this equation, I get this. What's 0 plus 1? 1. What's the absolute value of 1? What's 1 times -1/2? And what's -1/2 minus 3? -3.5. So my input was 0, my output is -3.5. So 0, -3.5. And what do I do with this point? Mirror it on the other side. There's my absolute value. Now in words, tell me how that compares to a parent function.
The vertex shifting
Ver-
down 3 plus 1.
Good. What else? It shrunk by what? Half, and then what else? And it flipped over the x-axis. Beautiful. That's what we're working on tonight.